Hey everyone, in this video we will be seeing how to simulate a cooling duct that can be used in a laptop to cool down the CPU. For this simulation and modeling, I have used Solid Edge 2026 version for the designing and 3D extrusion of the cooling duct. And for CFD simulations, I have used SimCenter Star CCM Plus 2025 version. So I will be showing you how the how I have modeled the cooling duct. Then I will show you how to simulate it in the Star CCM Plus. So first there is the base plate in which the CPU will be the base plate is just above the CPU, and we can see the fins. I have constructed the fins in a way that the air goes through every fins, and we can see the fluid region where the water can come in and get out. So I'll saving this as step file. As you can see, Uh, as I have already saved it, I'm not saving now. I'll just cancel and close this window. And now I will be opening Star CCM Plus. So this is the window you will see once you open it. Now I will be importing the CAD model for our simulation. Uh, Now it is loading. Before it, we should uncheck the merge paths, check paths visibility, and we should change the density into fine, very fine. Yes, and then it is loading. Then you can see the window where we can see the base plate and the fluid region. Yes, this is the CAD model. So now we will open the geometry tree and we will check both the parts are both the different bodies are visible. So we rename the base plate as solid metal and the fluid region as fluid alone. Now next what we'll be doing is we will separate the fin fins from the fluid domain so that the fluid will not flow over the fins and it will act as walls. So the operation is done. This is the Boolean subtract that is available. You can also do it in the CAD softwares, but sometimes it may leave some residual which will affect the mesh quality. So now we should create the paths like inlet outlet so that we can give the boundary conditions. So we should split by patch, and we should select the inlet, then create, and then similarly we should do for the outlet region also. So the outlet, yes, then create, then we'll close this one because we don't have any other boundary conditions here to assign. So just close this and we'll move to the fluid region. And for the fluid region we should do as same, sorry, for the base plate we should select the CPU, near CPU region as the heat source. We name it as the heat source and then we create, then close this. So we should execute the subtract again so that the created parts will be updated into the new part as subtract, and we rename it as air domain. Once we have completed creating parts and naming them, we can create region so that we can further mesh the solid metal and the fluid region. Yeah, we can see the. So now we will coming to mesh. So first we will mesh the solid metal. For this we will choose surface remesher and trim cells. So we should change the base size into 1 mm, which will be default as 1 meter. Yes, and then we'll just execute it. That's no other changes. It will take some time for meshing. It depends upon the size and volume. We can see that the mesh is completed. Now we will mesh the air domain. For this we will include the prism layer also. For the base size we will change it into 1 mm again, and the target surface size into 60. Sorry, it's 60. And then we'll change the minimum surface size to 4, and the prism layer will be having 5 prism layer with stretching ratio as 1 is to 3, and the prism layer thickness I'm setting it as 2 mm as we have very thin fins. The maximum size will be 50% of the base size, and then we hit the execute button to mesh. This may take some more time than the previous mesh. To visualize the mesh, we can go to scene plot, which is near the simulation, the left side of the simulation tree. We can go there and we can change the surface. We should select the surface and we should enable the mesh options. So in this region, you can see the meshing status. You can see the output of the meshing operations here. You can see the cell numbers, how much the quality is, what the operations have done to the mesh. Yes, we can see the mesh is completed. So for viewing the mesh, we will do as follows. Here we should check the mesh checkbox along with others so that we can view the mesh. We can see the hexagonal mesh. So to fully view the mesh, we will untoggle the view of the base metal so that we can see the mesh of the air fluid region alone. So we have completed the meshing. Now we should include the physics for the metal, solid metal region and fluid region separately. So for the first one, we should choose gas with segregated flow. We use ideal gas for this, and also segregated fluid temperature with steady state time with laminar flow. Then we will close this window. We choose the laminar because 3 meter per second in this regions will come under laminar conditions. So for the solid metals, we choose solid with three-dimensional and steady state, and we use segregated solid energy with constant density. For changing the material, we'll just go to air, then right click, we can replace it. I'm simply leaving to air with room temperature, so I will not be changing anything here. Coming to solid metal, I'll be the default material which will be is aluminum. I'll be replacing this with the copper for better thermal exchange. Once this is done, we can go to regions, and for each region we should assign the appropriate physical models that we have selected. For this we can see that the air domain we have the proper air physics. Then for the solid metal we should change it. Now we should open the boundary folders and we can see the inlet outlet. So we should change the inlet property as velocity inlet, and then we should give the physical values for this, that is 3 meter per second. After changing it, and we can see the temperature as 300 Kelvin, which is the 27 degrees Celsius, which is the room temperature. And for the outlet we choose pressure outlet, and the rest is as same. Coming to the solid metal, we can see the heat source. We can change the thermal specification as heat flux and change the physics value to 200,000. So this is basically the value which we can get while operating the laptop under heavy usage. So you can find these values in any internet. So now what we should do is, there is no um, interface between the solid metal and the fluid region. So what we will be doing is we should connect the common boundary regions of these two bodies, that is the fin parts of the both bodies. So we can clearly we should choose one. See, we can see the colored face, which is the fins of the fluid region, and the colored face of the solid metal. So we press Control and select both this and create interface, which will create the interface for our simulation. We can see it, and then we close the regions and interface also, and we have done giving the boundary conditions and meshing. So for simulating and viewing the results, we first create a section plane normal to y-axis, so that we can visualize the velocity contours and temperature contours for every iterations. We I set the stopping criteria to 5000, and then I create a new scalar scene so that I can get the velocity contours. So I should choose the derived part in the part section so that we can see the fluid motion in that region alone to get a better visualization. You can clearly see it. So I'll be choosing axial velocity as the function, and I will be creating another scalar scene for visualizing the temperature contours. We can see this also here. So the same we should do for selecting the derived part. Here you can see the part. Then I will choose the function as temperature, then click OK. Yes, and then we'll start running the simulation. So here we will have the residual. Now it is initializing. Once the initialization is completed, the iteration phase will start. As you can see, the iteration starts. So for the first iteration, we can see the heat from the CPU area. So for each iteration, we can visualize how the temperature goes from the CPU region to other base plate and the fin. We can clearly visualize it, and we can see the reverse flow, but it is not a big concern as the flow after near the outlet is we are not considering it as much, and the reverse flow is related to the mass flow outside the regions. We stop the simulation and we create a new report uh, for maximum. So we should choose the field function as temperature, and then choose the part as solid metal so that we can get the uh, maximum heat that the solid metal has. So we can create the plot for that same, and then we run. So you can clearly see the temperature rise in the nearby regions of the solid metal. We can see the residual. It should keep going down. We can see the maximum monitor plots, which should Yes, and the temperature contours in real time can see this. This is our geometry and not this one. Yes, this is our velocity contour. This was this is what I was telling about the after the fins. We are not gonna consider it as much how the flow is near the outlet. So you can we can see the simulation iterations. We can see changes with every iteration. So here the residual must keep going down. Even if it fluctuates, it should go down the graph. And also in this maximum temperature graph, the graph should go horizontal, which means that the heat intake is equal to the the heat gained is equal to the heat lost. So then we can know that the simulation is complete. So that will be the maximum heat range that the CPU can produce, that the base element can handle. So once the simulation is complete, we can see the residuals as near the 100,000, near the 100,000th iteration the complete. We can see that for more above 6,000 iterations, it's 395 Kelvin. We can see the heat distribution. uh, yes, you can clearly visualize it. These are the fins, and these are the velocity contours. uh, you can see that how the velocity goes. So these are the streamlines which can be created by right clicking the derived paths. You can visualize it. We can change it to temperature for temperature visualization. Yes, you can see near the fins it is very hot, and in the other regions it is cool. It is running cool. Thank you for watching this video.